In this presentation, I will be explaining the analysis of single phase fully controlled rectifiers. Now let us see the analysis of a single phase full converter or with RLE load. Suppose this is the circuit diagram in which we are giving a single phase input supply, and this is the load what we are considering. It's an RLE load, resistance, inductance, and a battery. And this is the converter that consists of 4 silicon control rectifiers, T1, T2, and T3 and T4. And the assumption is in this one is that load current is continuous and ripple free, and that is load current I0 equal to constant I0. So the current flowing through this RLE load is a constant current, that is this one. Say constant capital I0 is the current flowing through this one. So because inductance value is sufficient to make this load current constant. That is output load current is a constant, is an assumption. Now coming to the waveform as such, the input voltage to this single phase full converter, that is this is the input voltage, sinusoidal voltage, and 0 to pi radians during that positive half cycle of the input. The thyristors T1 and T2 are forward bias. Therefore, when this is positive, here it is equal to, of course, this is this with respect to this point, this is positive. That is, we are this one here. Therefore, this is getting forward bias. T1 and T2 are getting forward bias. Therefore, during that period, you can trigger T1 and T2. And once T1 and T2 conducts here, it is just like a closed switch. That T1 and T2 acts just like a closed switch because we are neglecting the drop across thyristor when it is conducting. Therefore, then the circuit is like this one. The current is flowing through T1 and through this RLE load, returning back to T2 and it's returning and it's coming to T. Therefore, this is the circuit diagram when T1 and T2 conducts. And at that time, the voltage across the RLE load is same as whatever the input voltage is, path like this one. Therefore, at firing angle alpha, the voltage is same as the input voltage that is coming here. And because of this inductance here, and here RLE load is considered here, that continues to conduct. That is, this devices T1 and T2 continues to conduct until the next firing to the T3 and T4 are given here. That is why here it is going to until pi plus alpha, the devices T1 and T2 are conducting. At pi plus alpha, here T3 and T4 are turned on, because during that period it is the negative half cycle of the input here. Actually, here the voltage is more, or this positive with respect to here. Therefore, here T3 and T4 are forward bias. T3 and T4 are forward bias during from the pi to 2 pi. Therefore, we are firing these T3 and T4 at firing angle pi plus alpha. That is fired at pi plus alpha here. And here, when these are being fired, that is T3 and T4 are fired here. Here you can say that here the voltage is positive with respect to here. Therefore, this is getting a reverse voltage. Similarly, here also you are getting a negative voltage. This is also getting a reverse voltage. Or these are the incoming thyristors. T3 and T4 are called the incoming thyristors at this instant. And outgoing SCRs are called T1 and T2 are the outgoing SCRs. Or when the incoming SCRs are fired, that will be reverse bias as the outgoing SCRs that gets turned off. So that now the path like this one, that is here through this one, through T3 and it's returning to RLE, and again it is coming to T4 and is returning back to here. Therefore, from pi plus alpha to again 2 pi plus alpha, here this T3 and T4 are conducting. T3 and T4 are conducting. Again, the voltage at this point equal to the voltage at this point with respect to this one. But what we are showing here is the voltage at this point with respect to this one. Therefore, here the voltage is just 180 degree out of phase, that one. That is why here they say, inverse of this voltage is taken here. That is why the output voltage is now positive. That continues until 2 pi plus alpha. This is called continuous conduction. And in this way, what we are assuming is that current through the RLE load is continuously I naught. This is a constant current flowing through this one. Therefore, again, that is repeating at 2 pi plus alpha, that continues. Therefore, from alpha to pi plus alpha, T1 and T2 are conducting. From pi plus alpha to 2 pi plus alpha, T3 and T4 are conducting. And all this time, the current through the load is a constant current, I naught is flowing. Now, if you watch the source current here, you can say that one, when T1 and T2 are conducting, the current is like this one, that is flowing, that constant current I naught is flowing. So the current is like in this direction. Now, when T3 and T4 are conducting, again this current is going to T3, and again the current through the load is same direction. But here you can say that source current is now reversed. That is why if you plot the source current here, it can say that it is equal to a square waveform. We'll be getting like that one. Therefore, this is during this period T1 and T2 are conducting. During this period T3 and T4 are conducting. Therefore, this is the current at the source side, and this is the load current, and this is the load voltage, and this is the input voltage. During this period T1 and T2 are conducting. During this period T3 and T4 are conducting. Now, if you calculate the average value of the output voltage here, average value is given by 1 by pi integral alpha to pi plus alpha Vm sin omega t d omega t. Or that's equal to, can say Vm is taken 2 Vm by pi cos alpha. Already derived that one. It is equal to 2 Vm by pi cos alpha, and that is the average value of the output voltage. And the RMS value of this voltage, if you calculate the RMS value of the voltage, which is given by root mean square value, square root of 1 by pi integral alpha to pi plus alpha Vm square sin square omega t d omega t. Or it is the square of this voltage and just taken the mean, and then we are taking the root. So that's why root mean square value, if you calculate, they will be getting, it is equal to Vm by root 2, which is equal to, the RMS value of this output voltage, that is same as the RMS value of the input voltage. For RMS value of the output voltage, the RMS value of the output voltage is given by same. We are deriving the same thing here. Whatever we shown is being derived here. RMS value of the output voltage equal to root of this one. Or if you substitute that one, sin squared omega t replaced by 1 minus cos omega t divided by 2. Of course, we will be taking Vm by root 2 into root of 1 by pi omega t minus sin 2 omega t by 2. Limits is alpha to pi plus alpha, and substituting in this equation, and we'll be getting it is equal to Vm by root 2, same as this one. Therefore, the RMS value of the output voltage, that is the RMS value of this voltage, that is equal to Vm by root 2, and the average value of this voltage is equal to 2 Vm by pi cos alpha, where alpha is the firing angle. This alpha is the firing angle. Now we are finding out the Fourier series of the function ft. What are the different frequency components in the source current? Source current is this one, but we have seen source current is equal to, this is this one. Therefore, from alpha to pi plus alpha, it is plus I naught. From pi plus alpha to 2 pi plus alpha, it is equal to minus I naught. Therefore, this is the source current. We are going to do the Fourier analysis or Fourier series, different frequency components. We want to extract that one. For that one, in general equation, is ft equal to a naught plus sigma n to 1, n equal to 1 to infinity, an cos n omega t plus bn sin omega t, where an equal to 1 by t, time period of that one, integral 0 to t ft dt. Just this is a generalized equation to find out the Fourier series. Similarly, an equal to 2 by t integral 0 to t ft cos n omega t, which is equal to, t means it is the time period. From here to here, it is equal to 2 pi. Therefore, it is equal to 2 by pi, 2, that is 2 by 2 pi into 0 to 2 pi ft cos n omega t d omega t. And bn equal to again 2 by t integral 0 to t ft sin n omega t, or it is equal to 2 by 2 pi into 0 to 2 pi into ft sin n omega t. And the phase, that is phase shift between this one, is given by, for different harmonics, that phase shift is given by phi n is equal to tan inverse an by bn. Therefore, this is a general equation for the Fourier series ft, where a naught is actually this is a 1 by t integral 0 to t ft dt. This is a DC quantity, and this is the sine component, this is the cosine component, and this is the of course sine component omega t sin omega t. Therefore, this is the phase shift phi n. Now there are different types of we can classify the function as even symmetry, has got a even symmetry. Even symmetry means this is having a even symmetry waveform. In that one, ft equal to f of minus t. Here this waveform ft equal to f of minus t. That is why it is called even symmetry. If this, in the case of even symmetry, when you are writing the Fourier series, the corresponding a0 equal to 2 by t integral 0 to t by 2 ft dt for even symmetry, and an equal to 4 by t integral 0 to t by 2 ft cos n omega t dt, and bn equals 0. Therefore, this is a0, an, and bn for an even symmetry type of waveforms. Similarly, for odd symmetry, in odd symmetry means that here this is an odd symmetry waveform in which ft equal to minus of f minus t. This is the ft equal to minus of f minus t. Therefore, that type of waveform is called having a even symmetry. Sorry, odd symmetry. It's called odd symmetry. In odd symmetry, if it is that one, a0 will be equal to 0, the DC quantity will become 0, and an is also equal to 0, and bn equal to 4 by t integral 0 to t by 2 ft sine n omega t. Therefore, waveform having a odd symmetry, these are the value of an, a0, an, bn. And if the waveform is having even symmetry, a0, an, and bn. Next, what we have already discussed in the previous slide, that is, this is having a half-wave symmetry. We call it half-wave symmetry. In half-wave symmetry, ft equal to minus of f of t plus t by 2. ft equal to minus of f t plus t by 2. T plus t by 2. Therefore, this is having a half-wave symmetry. In this case, a0 equal to 0 and an equal to 4 by t integral 0 to t by 2 ft cos n omega t, where n equal to odd, and bn equal to 4 by t integral 0 to t by 2 ft into sine n omega t, where n is equal to odd. Therefore, these are the quantities of the Fourier constants like a0, an, and bn for a half-wave symmetry, having a waveform like this one, in which ft equal to value of the function at any instant t equal to value of the function t plus t by 2. Of course, it is equal to minus of that one, minus ft plus t, t plus capital T by t is the time period. Capital T is the time period. That is from here to here. That is called the time period. Therefore, this having a odd symmetry, this is the equation for the Fourier constant like a0 equal to 0, an equal to 4 by t integral 0 to t by 2 ft cos n omega t, when n equal to odd, and bn equal to 4 by t integral 0 to t by 2 ft sine n omega t, where n is odd. Therefore, like that, here there's a quarter wave symmetry also there. Therefore, these are the equation for different Fourier constants for different types of waveforms. Now, continuing the analysis of single phase full converter with RLE load and Fourier analysis of the source current. This is the source current. This is the source current. Actually, this is equal to alpha. This is equal to pi plus alpha. This is equal to 2 pi plus alpha. We have to analyze this source current. What are the different frequency components in this source current? And for that one, as we have already seen here, this ft equal to a0 into sigma n to 1 to t n cos n omega t plus bn sin omega t, the general equation for the Fourier series. And here, equation for a0 already we have seen, equation for an, and here bn, and this is the equation for the phase shift between these components, cosine and sine component, phase shift equal to tan inverse an by bn. Now, this n can be from 1 to, here n can be 1 to, of course, infinity. It's called the frequency component. For example, if n equal to 1, it is called fundamental quantity. For if you are considering n equal to 1, it is a1 cos omega t plus b1 sin omega t. Now, if n equal to 2, it's a second harmonic, a2 cos 2 omega t plus b2 sin 2 omega t. Therefore, the n can be varied from 1 to infinity, in which the Fourier constant like an, bn, and a0, that general equation is this one, and bn, a0, and this one, and the phase shift between these cosine and sine, which is equal to tan inverse an by bn. For example, the fundamental phase shift means phi n equal to 1. Phi 1 equal to tan inverse a1 by b1. Therefore, therefore the source current, in this case, the function ft is given by the source current, is. So we want to analyze the frequency component of the source current. Therefore, ist equal to a0 plus sigma n equal to 1 to infinity an cos n omega t plus bn sin n omega t. The different Fourier constants a0, an, and bn. Now, continuing the analysis here, the Fourier analysis of source current here. This is the source current. This is from alpha to pi plus alpha plus I0, pi plus alpha to 2 pi plus alpha minus I0. We are going to analyze this, do the Fourier analysis of this source current. and the source current IT equal to A naught plus sigma n1 dt infinity n cos n omega t plus bn sin omega t. And here this is having a half-wave symmetry, as we have already seen, ft equal to minus of ft plus t by 2. That is why it is called a half-wave symmetry. If it is having a half-wave symmetry, it is equal to, we can say that one, A naught will be equal to 0, and here an, here A naught equal, actually equation for A naught is this one, but in half-wave symmetry A naught will become 0, and an equal to, as half-wave symmetry, the equation equal to 4 by t integral 0 to in the, no, here no 4 by t in 4 by t, that is changing from alpha to pi plus alpha, 4 by t alpha to pi plus alpha, and this magnitude equal to I naught cos n omega t d omega t, and which is equal to, if you do the, I mean, we'll see that later, that integration, this one will be getting minus 4 I naught 2 by n pi sin n omega t, where n equal odd. For even it is equal to 0, but when it's equal to odd, this equation for an equal to, that is meaning that here a1 can be, if you put n equal to 1, a1 equal to minus 4 I naught divided by pi into sin alpha, and when odd it, n is odd and even n2 is not there, then we can have a3 equal to a2 equal to 0, and a3 equal to, we can say it is equal to 4 I naught divided by 3 pi sin 3 alpha. Like that you can calculate. Therefore, similarly, an and bn equations are there, and phi n equal to tan inverse an by bn. Now, derivation of this equation, an can be derived as an equal to 4 by 2 pi integral alpha to pi plus alpha I naught cos n omega t d omega t, which is equal to 2 I naught divided by n pi into sin n omega t into alpha to pi plus alpha, or 2 I naught divided by n pi sin pi plus alpha minus sin n alpha, and psi n pi plus alpha equal to minus n and alpha when n is equal to odd, and psi n pi plus alpha equal to sin n alpha if n is equal to odd, sorry, even. Therefore, here an equal to minus 4 I naught divided by n pi sin n alpha, even that will be getting 0. For if n is odd, an equal to minus 4 I naught divided by n pi sin n alpha, and it is 0 if n is equal to even. And similarly, you can derive for the bn also. Here, same way you can derive the bn, and you will be getting it is equal to bn equal to 4 I naught divided by n pi into cos n alpha if n is equal to odd. If n is equal to even, that bn equal to 0. Therefore, it is equal to 0 if n is equal to even. Therefore, if we can say, if n equal to 1, b1 equal to 4 I naught divided by pi into cos alpha, where n equal to 1, a1 equal to minus 4 I naught divided by pi into sin alpha. Therefore, you can calculate the fundamental, Fourier constant corresponding to the fundamental signal, like a1 equal to minus 4 I naught by pi sin alpha, and b1 equal to 4 I naught divided by pi cos alpha. Therefore, by substituting value of the n, or if you put n equal to 1, you will be getting a1. a1 equal to minus 4 I naught divided by pi into sin alpha. Similarly, corresponding to n equal to 1, b1 equal to 4 I naught, that is substituting here, it is equal to 4 I naught divided by pi into cos alpha. That is the Fourier constant a1 and b. Once you calculate the Fourier constant a1 and b1, then we can calculate what is the maximum value. This corresponding to the fundamental signal, because when n equal to 1, that corresponds to fundamental signal. And the maximum value of the fundamental can be calculated as square root of a1 square plus b1 square. Square root of a1 square plus b1 square is the maximum value of this fundamental. Now to find out the RMS value of the fundamental, square root of A1 square plus B1 square divided by root 2. Therefore here, if you substitute this value of A1 square and A1 and B1 in this equation, you will be getting it equal to 2 root 2 I naught divided by pi. Therefore the RMS value of the fundamental signal, which is equal to 2 root 2 I naught, this is I naught, 2 root 2 I naught divided by pi. And similarly, the phase shift between this phase shift, which is corresponding to the fundamental quantity, what is the phase shift? Phi n. From this one, what is the phase shift of the fundamental, which is equal to tan inverse phi n equal to tan inverse a n by b n, or corresponding to fundamental phi 1 equal to tan inverse a1 by b1. For tan inverse this one by this one, we'll be getting it is equal to tan inverse tan minus alpha, or it is equal to minus alpha. Therefore the phase shift of this fundamental equal to phi 1 equal to minus alpha, and the RMS value of the fundamental is given by 2 root 2 by pi into I naught. That is the RMS value of the fundamental signal, that is derived from the Fourier series. And the RMS value of the source current, what is the RMS value of this current? Say square wave current will be getting, or so rectangular waveform you are getting, and what is the RMS value of this one? In order to calculate the root mean square value of this source current, square root of 1 by pi integral alpha to pi plus alpha this I naught square d omega t. Then you will be getting it is equal to I naught. Therefore, the RMS value of this source current equal to I naught, and the RMS value of the fundamental current, which is equal to 2 root 2 I naught divided by pi. In this one, we'll be defining different parameters like displacement power factor, distortion factor, power factor, then total harmonic distortion THD. Now, displacement power factor is the cosine of the angle between the fundamental voltage and fundamental current. That we have already seen. Phi 1 we calculated in the previous slide. Phi 1 equal to tan inverse A1 by B1, and we calculate it is equal to minus alpha in this case. Therefore, the displacement power factor is the cosine of the angle between the fundamental voltage and fundamental current, which is equal to cos phi 1, that is dPf. And distortion factor is a ratio of the RMS value of the fundamental to the RMS value of the total waveform. Therefore, distortion factor is that IS1, it is the RMS value of the fundamental divided by the RMS value of the total signal, IS. That is the distortion factor. And the total power factor is the ratio of the fundamental active power to the total apparent power. Fundamental active power is that Vs into IS1 into cos phi 1. That is the fundamental active power. That divided by the apparent power, that is equal to V into I. Actually, it is equal to Vs into Is. Now, if you calculate, this is equal to IS1 divided by Is, or the RMS value of the fundamental divided by the RMS value of the total signal into cos into phi 1, or this is IS1 divided by Is. That is, this is called a distortion factor, and cos phi 1 is called the displacement power factor. Therefore, the product of distortion factor and displacement power factor, that is called the power factor of this circuit as such. Therefore, the power factor is equal to dF into dPf. And the next term to be defined is that total harmonic distortion. Total harmonic distortion is defined as the ratio of the sum of the powers of all harmonic components to the power of the fundamental, the power of the fundamental frequency, or meaning that what is the harmonic content. In terms of current, we can write that what is the harmonic content divided by what is the fundamental quantity. Therefore, related to the fundamental, how much harmonic is there? That ratio represents the total harmonic distortion. Therefore, to find out the harmonic component, square root of Is square is the RMS value of the total signal, minus this is RMS value of the fundamental. If you subtract the fundamental Is1 square, then we will be getting the numerator is the RMS value of the harmonics. The numerator is the RMS value of the harmonics, and this is the RMS value of the fundamental. Therefore, how much harmonic is there related to the fundamental, that indicates the total harmonic distortion. Therefore, the total current can be defined as the ratio of the sum of the harmonic component of the current to the fundamental current component, that is RMS values. That is square root of is square minus is1 square divided by is1. That is what is called the total harmonic distortion. For the continuing the analysis of single phase full converter with RLE load here, this is the source current as already we have seen. That is from alpha to pi plus alpha, it is plus I naught. From pi plus alpha to 2 pi plus alpha, it is equal to minus I naught. We are analyzing this source current and we found that apart from the fundamental, there are harmonics also there. And what we are concentrating is that displacement power factor is the power factor of the fundamental corresponding to fundamental. That is cosine of the angle between fundamental voltage and current. That is called cos phi 1, which is equal to cos of phi 1 equal to minus alpha, or it is equal to cos alpha. Therefore, that is called the displacement power factor, and distortion factor equal to is1 divided by is. That is RMS value of the fundamental divided by the total RMS value, the RMS value of this rectangular wave. That is equal to 2 root 2 I naught divided by pi. This is RMS value of the fundamental. That divided by RMS value of the total this signal, which is equal to I naught, or 2 root 2 divided by pi, 0.9003. Therefore, this is the distortion factor, and displacement power factor equal to cos alpha, where alpha is a firing angle. Therefore, the total harmonic distortion is given by square root of is square minus is1 square. Therefore, this is the harmonic content, RMS value of the harmonic content, divided by RMS value of the fundamental, is1. Or it is, if you substitute here in this same equation, I naught square is the RMS value of the total RMS value. That is, is the RMS value of the total source current. Therefore, that is equal to I naught. For I naught square minus 2 root 2 I naught divided by pi whole square. That is RMS value of the fundamental divided by RMS value of the fundamental, 2 root 2 I naught divided by pi. This will be getting 0.483. For the total harmonic distortion equal to 0.483, or in terms of percentage, if you express, it is equal to 48.3 percentage. THD equal to 48.3 percentage, and as a this is the distortion factor equal to 0.9003 and cos alpha. Therefore, the total power factor is equal to, as you know already think, it is actually the product of a distortion factor and displacement power factor, which is equal to same equation as already we have seen, which is equal to distortion factor and displacement, that is is1 divided by is into cos phi 1. Therefore, actually, this is the active power to the apparent power, is1 divided by s into cos phi 1, displacement power factor into distortion factor. If you substitute here and this one, it is equal to 2 root 2 pi into cos alpha. And this, I mean, if you total harmonic distortion can also be written as, which is equal to is square minus is1 square divided by is1, or we are reducing that one, we can get as total harmonic distortion. If you square it, that total harmonic distortion equal to is square minus is1 square minus 1, or is1 divided by is is equal to distortion factor. Substituting that one, therefore TH, total harmonic distortion, can be derived in terms of distortion factor as TH, in this case, or distortion factor can be TF square in 1 by 1 plus THD square, or distortion factor in terms of THD square root of 1 by 1 plus THD whole square. That's one more equation is relating the distortion factor and total harmonic distortion. Therefore, these are the parameters: displacement power factor, distortion factor, and total harmonic distortion. In this case, that is of the source current. Therefore, and the A1 equal to minus 4 I naught divided by pi sin alpha. B1 already we are derived 4 I naught divided by cos alpha. Therefore, phi 1 equal to tan inverse A1 by B1. That is why we are getting it is equal to minus alpha. That is substituted here. Therefore, that is we are getting cos minus alpha equal to cos alpha. Therefore, this is a displacement power factor. This is a distortion factor. And this is a total harmonic distortion. Now, continuing the analysis of single phase full converter with RLA load. Already we have seen that the fundamental phase shift phi 1 equal to minus alpha in this case. And fundamental RMS value of fundamental equal to 2 root 2 by pi into I naught, and total RMS value of this one equal to I naught, is equal to I naught, and distortion factor equal to RMS value of this one divided by is, and similarly power factor equal to the product of distortion factor and the displacement power factor cos phi 1, or cos phi 1 means it is equal to cos alpha. Therefore, already we have derived this one. For a firing angle of 60 degree, if this alpha equal to say 60 degree, and a constant load current of 10 amperes, if you consider this a 10 amperes and this is equal to 60 degree, calculate the displacement power factor, distortion factor, and power factor, and total harmonic distortion. Let us see all those things. As an example, in a single phase full converter with RLE load, firing angle equal to 60 degree, and the load current equal to 10 amperes. This load current equal to 10 amperes, and the firing angle equal to 60 degree, and you are asked to find out what is the displacement power factor, what is the distortion factor, and what is the power factor, and what is the total harmonic distortion. The current equal to, this is equal to 10 amperes, constant current time. Firing angle equal to 60 degree. Therefore, the displacement power factor already we have derived, it is equal to cos phi 1 equal to cos alpha. Therefore, that is equal to cos 60 equal to 0.5. That is the displacement power factor. And distortion factor is given by the RMS value of the fundamental divided by total RMS value. Therefore, it is equal to, we have 2 root 2 I naught divided by pi into I naught, or 2 root 2 divided by pi, 0.9003. Therefore, this is a distortion factor and this is a displacement power factor. The product of this one, that is displacement power factor and distortion factor, that is the total power factor, which is equal to 0.5 into 0.9003, which is equal to 0.45. That is the, at the input side, if you see that one, the power factor is given by 0.45. If the load current equal to 10 amperes and the firing angle equal to 60 degree, the total power factor is given by the product of displacement power factor, which is equal to 0.5, and distortion factor 0.9003, and the total power factor becomes 0.45. Now to find out the RMS value of the current, already we have derived all those things. RMS value of the current IS is given by, total, this RMS value of this total input current we have derived previously. It is I naught only, which is equal to 10 amperes. And we have calculated, and here A1, which is equal to 4 I naught divided by sine 60, and which is equal to 11.01. And similarly, B1 is calculated. Then RMS value of the fundamental quantity is equal to, square root of A1 square plus B1 square plus root 2, or which is equal to 9 amperes. That is RMS value of the fundamental equal to 9 amperes. And the total harmonic system, the total harmonic distortion is given by square root of IS square minus IS1 square divided by IS1, or substituting that one, we'll be getting it equal to 0.48, or total harmonic distortion equal to 48% in this case.